Impulse. Now, this is a lecture about how time influences momentum, and really this is a science about the way in which things crash. By the end of this lecture, I hope that we can use the impulse formula to establish why it is divers actually jump into pools of water. Now, I know it seems kind of silly, but why do divers actually dive into pools? But if we take a look at this footage of an Olympic diver jumping off of a 3-meter platform as she enters the water, you'll see that right here her hands start to go in the water and then the rest of her body, and she very quickly goes from a high rate of velocity down to a low rate of velocity. So why do divers fall into water rather than the ground or onto concrete? And to be honest, this is a harder question to answer than you think. I mean, you've seen it so many times and it makes a lot of sense, but can you explain why you want to go into water? Now, a lot of students will say, well, water's a liquid, and I agree with them, but why is that important? Oh, well, it moves out of the way, and that's important, I agree with them, but it still doesn't answer the question of why. And really, the question becomes, it takes much, much longer. Because depending on how you interpret the amount of time from here to the point at which she stops, you could interpret this as anywhere from 0.800 to 1 second. And would you buy that? 1/1000. That's about how long it takes you to stop in water. Yeah. Well, here's our first problem. The woman in this video and my son Ethan jumps from a 3.0 meter platform. How fast are they moving the moment that they hit the water? Well, this sounds like a phenom problem. All right, what is given to us? We do know that the platform is 3 meters above the water. So my distance in the y is 3.0 meters. But here's the thing. The people are traveling in a downward direction. And why is that important? Because that helps us with a sign. One of our signs telling us that we're moving in a downward direction is a negative. So I need to have a negative displacement. What else do I know? Well, for a split second, Ethan and this woman are not moving. So I know that their velocity is 0 meters per second. And I know that the woman and my son are going to move at negative 9.8 meters per second squared. They're going to accelerate towards the center of the Earth. And here it's asking how fast. So that is a measurement of velocity. Question, meters per second. And so, which equation is going to help us? We're looking at a phenom, and so velocity final squared equals velocity initial squared plus 2 times acceleration times displacement. So when I substitute and simplify, I don't know what velocity squared is, but I do know that velocity initial is 0, and 2 times the acceleration of negative 9.8 times negative 3.0. Well, this blows up because any number times 0 is 0, and I get velocity final squared equals 58.8. And in order to get rid of the square, I'm going to take the square root of the left and the square root of the right. I get a velocity final that equals 7.6681115. But if we're being pleasant in my class, why don't we just say 7.67 meters per second. So okay, is my son moving pretty fast? Yeah, 7.5 meters in every second. He is moving really, really, really fast. Well, let's change it up a bit and remember this number, because Ethan, my son, jumps from a 3-meter platform. He does it again, but now I know that his mass is 29 kilograms. What is his momentum when he hits the water? Now from the last problem, I know that his velocity as he enters the water is 7.67 meters per second. But now I have a mass as well. That's 29 kilograms. What am I looking for? I'm looking for momentum. And that is in the units kilograms times meters per second. And the formula that I'm going to use is momentum equals mass times velocity. Now I don't know what momentum is, but I do know that mass is 29. And I'm going to multiply that by how fast he is going, 7.67, and I get a momentum of 222.43 kilograms times meters per second. So he has a lot of momentum when he hits the water. But now, when he stops moving in the water, when his velocity equals 0, what can we say about his momentum? Hey, his momentum equals 0 as well. And so here lies the problem. Ethan, my son, needs to change his momentum from 222.43 kilograms times meters per second all the way down to 0. He's got to do it somehow. And this is where the water comes in. Now, this concept of changing your momentum, we've talked about just a little bit, but now let's put it in the perspective of how long it takes. Impulse. Impulse is a measurement of how much force is applied over a time in which you are required to change your momentum. Now, there's a formula, and that is impulse equals force times time, or also known as F times T. Its units are newtons, the units for force, times seconds, units for time. And since we're talking about changes in momentum, we have a giant string of equations here that are all equal to each other. And I believe it's called the distributive property that tells you that if impulse is equal to change in momentum, and change in momentum is equal to delta P, or this triangle rho, that means that triangle rho is equal to impulse, or impulse is equal to force times time, or momentum final minus momentum initial. And so you can swap these in and out any way that you want. They're interchangeable. They're very much like Legos. You can take them apart. Well, let's see how that helps me in my circumstance with Ethan. Now Ethan, my son, he jumps from his 3-meter platform again, but this time I find out that it takes him 0.930 seconds to slow down so that his velocity is 0. How much force does his body actually end up experiencing? Well, I do know a couple things. I know that his momentum initial equals 222.43 kilograms times meters per second. And I do know that his momentum final equals 0 because I know that he's not moving anymore. Okay, let's see. I also have a time from the problem, 0.930 seconds. I actually have a velocity, and I'll write it here, but to be honest, it's not going to help me that much. And that's not too bad. I mean, in the givens, if you put too many givens, that's better than not putting enough. The thing that I'm looking for is force, and that's in newtons. And now I need to figure out an equation. And if I look here, I can see that let's see. I don't think impulse is really going to help me, or change in momentum, or this triangle P, because none of my givens. But if I look, force times time, that's going to help me. And then I have change momentum final minus momentum initial. All of those things are going to help me in my solving of my problem. So I'm going to say that force times time equals momentum final minus momentum initial. Now I don't know what force is, but I do know that time is 0.930 seconds, and that equals my final momentum is 0 minus 222.43. Now I know that this just kind of blows up. Adding 0 to anything is kind of, it doesn't help you that much. And so I'm going to have 0.930 times force equals negative 222.43. I'll divide the left by 0.930 so that these cancel. And whatever I do to the left, I have to do to the right, leaving me with a force of 239.17 newtons, which is a moderate amount of force. It, Ethan feels it when he hits the water, but what happens if he lands on concrete and he slows down in 0.009 seconds as opposed to 0.9 seconds? I'm going to take this formula and replace one number, force times 0.009 equals negative 222.43. In order to get force all by itself, I'll divide by 0.009. Cancel. The amount of force Ethan feels from the concrete would be, which is considerably more, 24,000 newtons. And what's interesting is there's an animal that exerts about 24,000 newtons of force downward, and that's a rhinoceros. And so in essence what this is saying is that if Ethan were to land on the concrete, he would experience the same amount of force as a rhino standing on my sun for a split second. But why? After we've done all of this, why is it that he experiences so much force here and not so much force here? It all comes down to time. You are forced to change your momentum. You are forced to change your momentum, but if you can change the amount of time it takes you to experience it, that means the difference between a wet and wild and fun day and a very bad day.